dimensional homomorphisms.
Great, thanks for the introduction. Yeah, right, my name is Ari. I'm a PhD student at the University of Münster in Germany. Today I'm here with my colleague Richard, and we want to present our approach of multidimensional homomorphisms and how we use it for array programming. Right, before we start, so just one quick introductory remark. So we have currently a paper undergraduate ACM Toplas, and that's actually a quite important paper for us. So there we describe our entire approach fully formally on more than 100 pages. And this talk aims to briefly highlight the main contributions that we are making in this paper. So this entire talk will be kind of an advertisement for this paper to hopefully gain the attention of the PLDI community. So we would really like to work a little bit more closely with you guys. And while the paper is quite formal, I don't want to bother you in the following with formal details, so I will rather focus on illustrative examples, and all the details and definitions, the formal ones, can be found and are provided in the paper. Okay, but now let's start. Okay, existing work. So I don't think I have to convince this community that array programming is already at the heart of many popular existing approaches. So we have, for example, TVM, Halide, and FireIron, which are scaling-based approaches, which we also heard in the talk before. We have popular polyhedral compilers, tensor comprehensions, PPCG, Pluto. And in this talk, or in our paper, we argue that the existing approaches currently struggle with achieving simultaneously performance, portability, and productivity. So I think three of the main goals that these communities currently striving for. And this is because, for example, if we look at scheduling-based approaches like TVM, these approaches usually achieve very high performance, but at the cost of their productivity. So they explicitly require the users implement so-called scheduling programs which express optimizations, requiring expert knowledge from the user. In contrast, when we look at polyhedral compilers, these are very productive, so they actually can even straightforwardly optimize and parallelize straightforward sequential C code, so that's most productive for most of the users. But therefore they struggle with performance, and similar issues apply also to other kinds of approaches. So the question now might be, so okay, why is it so challenging to achieve simultaneously performance, portability, and productivity? So for example, if you look at performance, for high performance, we need to have hardware-specific code optimizations, we need data-specific code optimizations. So we have to efficiently explore the core hierarchies of architectures, the memory hierarchies, we have to respect data layouts, data sizes, and so on and so forth. But when we now look at portability, to achieve portability, we need to be flexible exactly in these kind of optimizations. And for productivity even, we need to free the programmer from all kinds of optimization decisions. So to quickly conclude this slide, to achieve simultaneously performance, portability, and productivity, or achieving these three goals, poses challenging and often even contradicting requirements on code generation and optimization. Okay, the goal of our work now. Okay, we want to achieve performance, portability, and productivity in one combined approach, and therefore we introduce three new major contributions in our paper, which are: first, we introduce a high-level functional representation, fully formally defined, that allows us to express data parallel computation, agnostic from any kind of hardware and optimization details, while still capturing all information relevant for generating well-performing code for different kinds of architectures. Second, we introduce a low-level functional representations, again fully formally defined, that enables explicitly expressing and reasoning about optimizations for the memory and core hierarchies of architectures, and that can be straightforwardly transformed to executable program code, for example in OpenCL, CUDA, or OpenMP. And yeah, last but not least, we also introduce a lowering process that fully automatically lowers an instance of our high-level functional representation to an optimized variant of our low-level functional representation. So optimized means for the particular hardware characteristics and also for the data characteristics. Okay, so what do we want to do in the following? So I want to briefly present you our three main contributions: our high-level representation, our low-level representation, and our lowering process. Then I briefly present some experimental results regarding each particular goal: performance, portability, and productivity. Then I conclude the paper, and finally we have dedicated one slide to future work because we think this work might be an interesting starting point for many future directions. Okay, and just to emphasize again, so this will be really a brief overview of our paper here. So for example, we have just 4 slides to describing our low-level representation, while we have an entire section of more than 70 pages with all the required formalism to describe it. Similar things apply to experimental results. I can just briefly show some highlights of the experiments. So there are a lot of details in the paper, so if this somehow gains your interest, you can check the paper and find more details there. But okay, let's start. So regarding our high-level representation, so while we have designed this representation, we had 3 major goals in mind. It should be uniform, minimalistic, and structured. So what does it mean? So with uniform, we mean our representation should be able to express any kind of data per computation without relying on any computation-specific building blocks. So we don't want to have building blocks in our language, for example, just dedicated to linear algebra routines, some, for example, just for stencil computations. And if someone comes up with a new class of computations differing from linear algebra or stencil, then we need to extend our language by new building blocks. So we want to avoid these kind of issues. Then we want it to be minimalistic. So minimalistic means we want to rely on as less building blocks as possible to keep our language small and simple. So small and simple for the user and of course also for us implementers. And we also want the language to be structured, which means we want to avoid complex compositions and nestings of the building blocks as much as possible, which further contributes to the simplicity of our language. Also, again, for the user and also for us implementers. So yeah, just one quick reminder. So data per computation, I mentioned that a lot of times. So what do we actually mean by data per computation? So how are they characterized? So any data per computation, we apply the same function f to each point in a multidimensional grid of data. And then we combine the results, the obtained results in the different dimension using so-called combine operators. So when just looking at the example of matrix vector multiplication, here the function f is a straightforward multiplication. So we apply multiplication to matrix and vector elements. Then we combine the results in the second dimension, so the so-called k dimension in the context of matrix vector multiplication via addition. And in the other dimension, we just straightforwardly concatenate them. So that's the way how we obtain the result vector. And yeah, our high-level representation now. Our high-level representation expresses any kind of data per computation, agnostic from any hardware and optimization details, using exactly 3 higher-order functions only, which are inView, mdhom, and outView. And here, just to briefly mention what they do. So inView transforms the domain-specific data representation. So for example, matrices and vectors, as in case of matrix vector multiplication, to an internal data representation. This is denoted as MDA here, meaning multidimensional array, so quite close to the workshop topic here. mdhom computes the data per computation, and outview is the counterpart of input view. It just transforms the internal data representation back to the domain-specific representation. So for example, an output vector. We're just looking at a particular instance of our high-level representation for the example of matrix vector multiplication. So what happens here? So inView captures the accesses to the input data. So here we say, okay, at each point ik, we access matrix element at position ik and vector element at position k. Then mdhom specifies or expresses the data per computation, which means, okay, to the matrix and vector elements, apply multiplication, concatenate them in the first dimension. That's denoted as a double plus in our approach, and sum them up in the second dimension. That's a plus here. And yeah, the output view is trivial in this example, but it can be used, for example, in other computations, like matrix multiplication to store the result matrix as transposed or the like. And yeah, in our paper we could show that our high-level representation is capable of expressing various kinds of data per computations, which often differ in major characteristics. So for example, we have expressed matrix vector multiplication, but also other kinds of linear algebra routines, matrix multiplication on transposed input matrices, batch matrix multiplication, and so on and so forth. But we have also expressed, for example, stencil computations, convolution-like stencils, Jacobi stencils, which differ significantly from linear algebra routines because they access neighboring elements in the input data, requiring different kinds of optimizations. Then we have also, for example, probabilistic record linkage, which is important in data mining and used to identify duplicate entries in the database. We have scan patterns, map-reduce patterns, histogram computation, and also maximum bottom box sum, which was a running example in the PLDI paper from 2019. Okay, that's actually everything that I wanted or can say for time reasons about our high-level representation in this talk here. So to quickly summarize, we wanted our representation to be uniform for all the different kinds of data per computations, and we achieved this goal by exploiting the common algebraic properties of data per computations, rather than relying on domain-specific characteristics and building blocks. We wanted to be minimalistic, and we achieved this by relying on only 3 higher-order functions. And we want it to be structured, so we always use inView, mdhom, and outview, and always functionally composed in the same order to express any kind of data per computation. And yeah, last but not least, we have a full formal foundation for our representation, and all these concepts are formally defined, discussed, and illustrated in our paper here. Okay. Okay, now our second contribution, our low-level representation now. The goals that we had in mind while we have designed our low-level representation have been, so we wanted to express in hardware and optimize decomposition and recomposition of data per computation, which means how can we make the problem smaller so that we can assign them, for example, to the memory and core hierarchies of target architectures, and then recompose the obtained intermediate results back to the final results. That's what we mean by decomposition and recomposition. And we want it to be straightforwardly transformable to executable program code, like, for example, OpenMP, CUDA, and OpenCL. So it straightforwardly has two advantages. So once the proving process, so when we can prove that our low-level program is correct, then this transformation step is obviously also correct. And then we argue that our generated code is also correct. And of course, it makes it very easy to implement backend, so besides OpenMP, CUDA, and OpenCL, if you want to extend our system. Okay. Now, just very quickly, on just one slide, how do we express decomposition to our low-level representation? So in our paper, we have many, many pages about that and a lot of formalism, but if we want to summarize this and speaking very technically, we express formally a multi-layered, multi-dimensional tiling approach, and for each tile we say, okay, how it is assigned to the core hierarchy of the target architecture and how it is assigned to the memory hierarchy of the target architecture. So who should compute that tile, which core, on which layer, for example, in CUDA, a block, a thread, a warp or something like that, and where should this tile be stored? And for example, in shared memory in CUDA, register memory, these kind of things. And that for both steps, so for the decomposition, so for the inputs you can say, and also for the outputs, which would be part of the recomposition. And code generation, I cannot dive into too much detail, but I want to mention it's just our code generation process is completely described in our paper, and it's based on an imperative style pseudocode notation. So this pseudocode notation should be kind of an abstraction for all these programming languages like OpenCL, CUDA, OpenMP, even C, C++, and these kind of things. That's all I can know about the low-level representation here. So to quickly summarize, so the major goal of this low-level representation is, okay, we want to explicitly express decomposition of data parallel computations of any kind, no matter of BLAS, stencils, or other kind of data parallel computations, for the memory and core hierarchies of state-of-the-art parallel architectures, GPUs, CPUs, and so on and so forth. We want to have it straight, or it can be straightforwardly transformed to imperative-style executable program code. And again, as for our high-level representation, it's based on a full formal foundation, and all these formal concepts are defined and discussed and illustrated in our paper here. Okay, maybe just as an interesting side note, so we can even visualize our low-level programs here. So we can exploit the design exactly to, no matter what computation we're expressing in our low-level representation, that we can get these kind of videos here to express what exactly is going on. So I won't explain this picture completely or this video, but you can see the input is tiled, it is computed, recomposed back to the final result. So if you're interested in kind of visualizations, you may want to check that. Okay. And now just one quick slide regarding our lowering process. So our lowering process is fully formally defined and it's fully automatic. So we lower an instant of our high-level representation, as we have seen, for example, for matrix vector multiplication, fully automatically to an optimized instance of our low-level representation. For example, optimized for an NVIDIA GPU and maybe matrix and vector sizes as used in deep learning. And our lowering process is generic in performance-critical parameters, and we choose them fully automatically using our auto-tuning framework ATF, which we have presented a couple of years ago at TACO. And this parameterization allows us to make this process fully automatic. So just to describe these parameters, these formal parameters in a more technical way. So, for example, we can auto-tune the tile sizes on different layers in different dimensions, input tiles, output tiles, and these kind of things. Then we can auto-tune how we exploit the core hierarchy. Do we want to, for example, parallelize outer tiles, inner tiles, input tiles, output tiles, and these kind of things. And similarly for the memory hierarchy. For each tile, we can fully automatically, not fully automatically, we can generically say which memory region to use. For example, do we want to use shared memory for larger outer tiles, for inner tiles, for input tiles, output tiles, and these kind of things. That's how we express optimizations. Okay, now regarding experimental results. So in our paper, we experimentally evaluate our MDH approach in terms of each particular goal that we had in mind: performance, portability, and productivity. We tried to choose among the most challenging competitors for us, so to make evaluation really challenging for our approach. So as scheduling approach, we have chosen TVM, which works for CPU and GPU, and it's gaining more and more attention in both academia and industry here. We compared to two polyhedral compilers, PPCG and Pluto. PPCG works for GPU, Pluto for CPU. Then we also compared to functional approach Lift, which also works for GPU and CPU. And we also compared to domain-specific libraries, which are actually currently beyond the scope of our work because they work at the assembly level, so they also incorporate assembly level optimizations, while we are currently operating at the higher CUDA or OpenCL abstraction level. Then we also try to pick 5 very different and also challenging case studies for us. So we have linear algebra routines, matrix multiplication, and matrix vector multiplication. We have 2 different kinds of stencil computation, Jacobi, which is a 1D stencil example, Gaussian convolution, a 2D example. We have an example from quantum chemistry, we have a data mining example, and we have also a deep learning case study because most of our competitors are highly optimized, especially for deep learning. Yes. Now, regarding our performance evaluation, so the performance evaluation in our paper is conducted via runtime comparison, and here on this slide I just present some highlights for our deep learning case study because this study is really the most challenging for us because, as I said, most of the competitors are highly optimized towards deep learning. And we have evaluated in the paper on 2 NVIDIA GPUs and 2 Intel CPUs. Here's just 1 GPU results presented and 1 results for 1 CPU. And for example, you can observe we achieve speedups over TVM of more than 2x in many cases, of more than 10x over PPCG, and even as compared to the hand-optimized libraries like QBLAS and QDNN, we achieve speedups of more than 2x in many cases. Yeah, we have some slowdowns as compared to TVM, but that's actually right now just for a technical reason. So our implementation just currently rides on the NVIDIA runtime compilation library, while TVM uses NVIDIA C compiler here. I don't know why these 2 different NVIDIA compilers perform differently, but if we choose NVCC for our implementation also, we just tried it for some use cases, we achieve the same results for TVM in all cases, and often even better results than these 2x here. Good. The portability evaluation. So the portability evaluation of our paper is based on the Pennycook metric. This metric has proven to be quite decent for portability evaluation like we have in our paper here. And I won't explain the Pennycook metric in detail, but here a value close to 0 means low portability, and a value close to 1 means high portability. So higher is better in this case, or in this evaluation part. And here we can observe, for example, that our approach achieves in all cases better portability than TVM, for example. And other competitors are actually not listed because they achieve the lowest portability of 0 only, because they are often limited to particular target architectures and often also even to application classes. So for example, QBLAS just works for GPU and just for linear algebra routines. And the productivity evaluation of our paper is based on intuitive argumentation because classical code metrics cannot be used meaningfully here. So lines of code or development effort are not very meaningful for these kind of short and concise programs that we use in our approach and also are used by the related approaches here. And here in our paper we argue that we achieve in most cases the same or maybe often even higher productivity than our competitors here. Okay, now to conclude the talk. So our major goal was to combine performance, portability and productivity in one approach. For this we have formally introduced program representation on both high level and also low level. And we have also introduced a lowering process that fully automatically lowers an instance of our high-level representation to an optimized variant of our low-level representation. And yeah, we have at least quickly seen on the slide some quick experimental results, and in our paper we have much more results. And we argue there that we usually achieve higher performance, portability and productivity than popular rated approaches, even including hand-optimized libraries provided by vendors. Now regarding future work, so we think this work provides a formal foundation for many interesting future goals, for example. So currently for our approach, for example, we target just individual data per computation. So we generate code for just 1 matrix multiplication, maybe just 1 convolution. But we are currently working on, and we have also interesting and encouraging work in progress results for generating code immediately for multiple data per computations immediately, so that we can apply optimization across the computation. So for example, a matrix multiplication followed by a convolution here. That's often called fusing optimization. Then we aim to support computations on sparse data formats. There we have also some early work in progress results, but they also look kind of encouraging. Then next point, yeah, since we have a full formal foundation, it would make sense to introduce an analytical cost model to accelerate or even avoid entirely the auto-tuning overhead that we are currently having in our approach. Then we are currently working with 2 master students in integrating our approach into MLIR to make our work better accessible for the community. Then we also want to target assembly level languages because then we can benefit also from assembly level optimization, similarly as QBLAS, QDNN and these kind of approaches. And yeah, last but not least, we also want to extend our approach towards targeting heterogeneous systems. So currently we can target any kind of homogeneous system, multi-device, multi-node, or at least our formalism tells us exactly how to implement the infrastructure for this kind of system. But for heterogeneous system, we need a slight extension there. So we need some kinds of dynamic vector distribution techniques and these kind of things. And that's also something we are just or have worked on with a master student and have some early work in progress results. So that's actually the end of my talk. So thanks for listening. We are grateful for any kind of feedback from everybody. And yeah, we are now, I think we have plenty of time left for questions. Thank you.
Hi. So in your deep learning experimental results,
Okay.
what were the data sizes that you were seeing against the hand-tuned libraries? Where were you seeing the performance wins versus the losses?
Okay, so we have chosen data sizes, so real-world data sizes from ResNet 15, VGG 16, and MobileNet from both, from the training inference phase, and we have usually picked the size that took the most, the size that cost the most runtime in the computation of these networks. And yeah, what was the other question?
Well, no. So I can't really see the numbers
Okay,
there.
yes,
So
yeah,
like you're saying, I see that your CUDA DNN or
exactly.
against
We have
BLAS,
three kind of networks. Then we have the training and inference phase, and that's, for example, for matrix multiplication and convolution, the input size that took the most runtime in this network while executing it.
And but I mean, you said in your summary there, you say you go from 0.91 to 2.67?
Exactly, that's the lowest speed up, also the slowdown we have seen, the worst one, and that's the best one that we
So
have seen.
what were the data sizes? How did the data size affect those speed ups across the results? So in other words, like as the data sizes got larger, did you speed up?
Oh no, I don't think there's a very regular pattern in it. I don't know these QBLAS, and they're optimized for some data sizes, for some not. I think they have different kind of kernels there. Sometimes you pick a kernel of them, then it performs quite well, sometimes not that well. We could not recognize any specific structures there when we perform every time better and some structure where we perform always worse.
So do you have an intuition then, sort of like, are you going to mostly be competitive? Like in this example, are you mostly competitive with BLAS, or is it mostly a little bit of loss and then some real wins, or is it mostly real wins and some losses? Like
You can see it here. So the dark.
I'm having trouble seeing that. So
maybe you can see the color difference. So every light gray means we are better, and dark gray means the competitors are better. Here, for example, we have standard QBLAS, so we have been better for the matrix multiplication in ResNet 15 in both phases, training and inference. We have a slowdown in the training phase of VGG 16. Then we have this 0.93, and we have again a speed up in the inference phase here. So just in one case we have been slower, and in three cases we have been better in these examples here.
And these are just one operation, they weren't like fused?
No, it's just one matrix multiplication, exactly as called in these networks. So there's nothing cherry-picked or something, so we have really intercepted the real calls from these networks, choose the matrix multiplication that took the most time, and then we have used this data size. So we really try to make the experiment challenging for us, so to really test our systems there, or stress our system.
This idea of having just one operator for doing basically the transformations on data reminds me a little bit of the with loop constructs of SAC. Is that something you can compare to?
You mean, okay, let me go to the slide. You mean this operator here?
Yes.
I'm not very familiar with SAC right now. I need to check that. I don't want to give a wrong answer, I don't know.
So as you mentioned, this is a field where lots of work has been done previously, and your high-level language is similar to, but also different from many of the other high-level languages that have been proposed. So you get pretty good results. So is that because of the better high-level language? Do you just have a better tuner? Is it your low-level language? What actually makes the difference here?
I see. I think one major difference between our approach and other approaches is we target these reduction dimension, often called in other approaches, more efficiently. So for example, we always, when we have a matrix multiplication, we also treat the k dimension, this addition dimension, completely like the other dimension. So we can fully parallelize it, tie it, everything we can do with that. That's one major difference. I think we have also better emphasis of the recomposition phase. So how do we store output results and these kind of things that's often neglected in other approaches. Then we have designed our language to be very competitive, not competitive, but it works very well with auto-tuning. For example, when you have something like TVM or this kind of thing, then you have to choose, okay, do I use shared memory, yes or not? So you have it inherently in it. But we can, for example, auto-tune it. So sometimes very counterintuitively, our auto-system decides not using fast memory regions, for example, in CUDA. We don't know why, but this performs better. While TVM, for example, always uses these memory regions. And these kind of smaller things make our approach often perform better. So it's not that optimization that we have, but a mix of many small things that achieve these performance results there.
Then I'll ask another question. So you mentioned you could also express scan. How do you express a high-performance GPU scan in your low-level language?
Okay, we have a small section about that in the paper.
The reason I'm asking is the state-of-the-art algorithms involve...
performance evaluation of the scan, I must admit. We have just for the case studies I mentioned here, so I don't know how good it performed. I think...
Okay, but the specific thing is that the state-of-the-art scan algorithms on GPUs involve non-determinism, and is your low-level language, does it allow non-determinism?
No, not. But we need to check. I don't want to give a wrong answer here. So we have expressed on the high level, but we don't have any performance evaluation of the scans. So we cannot say what we are generating actually because we haven't tried it yet and compare it to other approaches. But it's also on our to-do list, definitely.
So you've got a lot of existing algorithms that you've implemented in your high-level representation. Do you have a feel for where it starts to get difficult? Like, can you do very efficient types of sorting and key-based table joins or things like that, or is that something that you would have to, like,
Okay.
where are the limits of this representation in terms of expressibility?
Okay, where was the slide? This one exactly. So what we can express efficiently are multidimensional homomorphisms. That's how we define this class of computations. And the multidimensional homomorphism tries to express exactly this. If the algorithm has these kind of structures so that you apply one function to a point in a multidimensional grid and then combine these grids via combine operators, that should work very well with our system. Sorting algorithm, if I remember right, the implementation, they consist of multiple these kind of steps. So you apply function f, you make some kind of combination, then you apply that again. So it's not very naturally for this. So that's how you actually define data parallel computation. So the question is rather, is the sorting algorithm really a data parallel computation in our sense here? If yes, then it should work. If not, then maybe not that well.
Well, I mean, do you have a sense of, if it's one of these more compound data parallel things where you have to compose a number of operations, do you have a sense of how well your system would be able to handle like sort of a complex composition of that versus, say, like one of the primitives like a radix sort or some of these quick sort, merge sort GPU algorithms that are handwritten?
For this, we need exactly this here. Then we have a lot of data parallel computation steps, and then we need to finish this part here, that we can generate code for these all these data parallel computation steps, and then our system should work quite well. So we have some encouraging results here. We have presented them as it was even a best poster nominee, so that should work at some point, and I think also quite well. But not now, not now.
Can I ask another one?
Yeah,
so what about synchronization? Do you do anything with like memory synchronization across data parallel computations or communication or anything like that?
We need to. It's not explicit in, let me go there. On this abstraction level, you don't see synchronization. But when we translate this to the executable code, that's where the synchronization points are injected. Oh, no, sure, we have time, I think, still.
Well, I think it's passed, so let's give the speaker another round of applause.
Thank you.